Okay, so basically when we talk about the properties describe the system actually. Properties are the descriptive characteristics of the system. You talk about pressure, temperature, volume, these are the properties. So properties are the coordinates to describe the state of a system. They are state variables of the system. So it's quite simple. Suppose I have to draw any plot, for example, PV diagram, and if I say the pressure is say 2 bar and the temperature is say 20 degrees Celsius, volume of the gas, if I am considering a gas, suppose that value is equal to 0.25 meter cube. So from pressure and temperature, I can always plot this particular point. So it could be here also. Okay. So here the value is 2 and here the value is 0.25. So basically properties are describing the state of a system. What is the state of the system is described by the property. Now what are the various properties of a system? The two types of the properties are there. The first one is the intensive properties and the second one is the extensive properties. So first of all, let us talk about the intensive properties. Intensive properties are independent of the mass of the system. For example, pressure and temperature. Now I will give you an example. Suppose we have a room here. Okay. In this particular room, if I measure the pressure and temperature, suppose pressure is equal to 1 atmosphere and temperature, let us say, is equal to 30 degrees Celsius. So I am taking the room as a whole. Now I can make few partitions in it. Say I make three partitions and I use different pressure gauges in different partitions. One pressure gauge is here, another pressure gauge is here, then there is another pressure gauge. And I also use different thermometers one here, and another one here. Okay. So what will happen? You can know by your experience that the temperature and pressure measured in each of the partitions will be same. That means the pressure in each partition will be 1 atmosphere, temperature will be 30 degrees Celsius. So there won't be any change in the temperature and pressure. So that means I have divided the mass in three parts. So each part is now having one third of the mass, but the pressure and temperature are still same. So pressure and temperature are two intensive properties. So there can be number of the intensive properties. It is not only limited to pressure and temperature. Okay. So one thing you should always remember: intensive properties are those properties which are independent of mass. Then let us talk about the extensive properties. Extensive properties are those properties which are dependent on the mass first of all. So for example, if I take volume, if I take energy, they are dependent upon the mass actually. More the mass of the system, more will be the energy. In the last example, as you have seen, if this is once again the same room and this is containing air, if I take this particular three particular partitions, if I say the enthalpy, you know, is a property. Okay, during your secondary school studies, you know, enthalpy is one of the properties. If I calculate the enthalpy of the partition 1, I calculate the enthalpy of the partition 2, and I calculate the enthalpy of the partition 3 individually, then you know that H1 will be different from H2, will be different from H3. Okay. But if I calculate the property in total enthalpy of the room, then it will be equal to I will say H1 plus H2 plus H3. That would be the total enthalpy actually. Okay. Now, uh, when I say extensive property, there is one more thing that you should remember actually. See, whenever I say extensive property, for example, if I am talking about enthalpy H, then it will be equal to M into H. If I will say, if I will take small h, okay, if I take small h, so small h has the unit kilojoules per kg. Okay, this is the unit for the specific enthalpy. So when I say intensive properties, they are specific in nature. Specific means they are independent of the mass, okay, or per kg of the mass. So when I am taking the enthalpy, okay, it is enthalpy. So capital H is enthalpy, whereas the small h stands for specific enthalpy. Okay, so specific enthalpy is represented by the small letters, whereas the enthalpy is represented by the capital letter because it is dependent upon the mass. So you can see this particular equation, H is equal to m into H. Now, what is the unit for the m? For m, the unit is kg. So when you multiply both these units, kg and kilojoules per kg, the kg and kg will cancel out and you are left with kilojoules. So kilojoules shows the total energy or total enthalpy of the system. Okay, so it means intensive properties are independent of mass, but when they are multiplied with the mass value, then you can get the extensive property, but that will not be valid in all the cases. For example, if you have pressure, you are measuring the pressure or temperature, and if you are mixing the mass, okay, then in the same quantity of the say if you are taking 1 kg of the air at 1 bar and at 30 degrees celsius, you are mixing 1 kg of more air at the same temperature and pressure, the pressure and temperature will not change. But in certain cases the property may change also. For example, enthalpy is energy, volume if you can consider, or if you can take any other property which is actually dependent upon mass, so that will increase. So sometimes when I talk about the intensive and the extensive properties, I will always define intensive properties by lowercase letters. So for intensive properties, I will use lowercase letters. You should remember this. And for extensive properties, we will use uppercase letters. Okay, uppercase letters. So as I told you, if I am saying specific enthalpy is actually uh, specific enthalpy is small h, whereas the total enthalpy is capital H. Okay, so you should remember this difference between specific properties and uh, total properties. So total properties are dependent upon mass. So basically, they are extensive in nature, and uh, specific properties are independent of the mass. That means they are independent. They are intensive properties. So specific intensive properties, when I say, so specific intensive properties is nothing but extensive properties per unit mass. We have divided those by mass. For example,
Excuse me,
specific
sir.
volume. Yes.
Sir, if we divide extensive properties by mass, so they are still not dependent on mass. So can't they be called intensive properties only? Like here,
No, no.
small h.
Then they will become specific extensive properties. Yeah, but they are intensive also. Specific extensive properties are intensive properties only. Okay.
Okay,
It
sir.
is written here. If you will see here, extensive properties per unit mass are intensive properties. For example, specific volume. Okay. Now, what is specific volume? Specific volume is volume per unit mass. Okay, and its unit is kgs per meter cube. Sorry, meter cube per kg. Okay. So, if you will take a room, or if you have a container, for example, if I am taking this particular container where you have a fixed volume, okay, where you have a fixed volume, say 2 meter cube, and the mass of the gas is suppose 4 kgs. So the specific volume, you take any partition, what will happen to the specific volume? Specific volume will be equal to zero point 0.5 meter cubes per kg. Okay, because we have to divide 2 by 4. So it will be zero point 0.5. You take any partition, but if you take the volume, then if you have made three partitions, then the volume of each partition, if they are equally divided, will be equal to 2 by 3, 2 by 3, and 2 by 3. Okay, it is clear. So intensive properties are independent of mass, whereas the extensive properties are dependent on mass. Now, when all the properties of a system have a definite values, the system is said to exist at a definite state. So it's quite simple. When I am talking about a thermodynamic system and I know about its properties, I know about the definite values. Like I told you, if I know the values, for example, as I told you earlier also, if I know the pressure and volume, I can always plot the state of the substance or state of the gas. Okay, so same is shown here also. Now suppose this is the initial state of the system. Thermodynamic system is existing at state point A. Now suppose you supply certain amount of the heat, or suppose the gas expands. What will happen? It will, the state will change to this particular location. It will be coming here. Then suppose it expands more, the volume increases. increases, pressure drops, the system comes to this particular state, then this particular state, and so on. You can follow different, the system may have different states. So ultimately it is reaching at this particular state. So what is happening, this is the process is actually, it is known as the change of the state of the system. So change of the state of the system means any one or two properties are varying actually. So once you know the variation in the properties, you can plot the next state and you know which path it is following. So path kya, see path is also very simple. If you are joining all the state points of the system, then you will get a particular path. For example, in this particular case, when we are going from A to B, I know that this is the path of the system. This is the path, and on this path there are infinite states, and when we are joining these infinite states, I am getting the path. So it is not necessary that I can go from point A to point B via this particular path only. The system can move from this path also, like this also. Okay, so it depends, the path will depend upon the change of the property or the change of the state actually. Okay, if the state changes in a different manner, the path will be different actually. So now let us talk about the process. If we know the path, exact path through which the system has gone, so that means I know about the process also. I know about the process. Now this is the process. There is a process which is going from A to B, going to take place from A to B. For example, it could be a constant pressure process. Okay, the system is undergoing a constant pressure process. So P is equal to constant. Then you can also have temperature is equal to constant. Then you can have volume is equal to constant. You can also have a adiabatic process represented by PV raised to power gamma is equal to constant. You can have a polytropic process represented by PV raised to power n is equal to constant. So all these are different processes. You can also have a process in which enthalpy remains constant. So there are different processes. Normally, when we talk about the constant pressure, we call it as a isobaric process. If we talk about the constant volume, it is isochoric process. Okay, if it is PV raised to power gamma is equal to constant, it is actually known as reversible adiabatic process. If it is temperature is equal to constant, then it is known as isothermal process. Okay, so I think you already know about the processes while preparing for your JE examination. You must have studied that in your undergraduate, means your senior secondary classes. Okay, now let us talk about the thermodynamic cycle. Suppose the system is at a particular state, say 1 initially, and it follows a particular path along this line. Okay, it reaches up to point number 2. So this is the final state of the system. Started from state point 1, went up to 2, and then once again the changes in the states are happening and the system goes along this particular path and reaches the initial state point 1. So what has happened, the system has gone under a thermodynamic cycle. So what is happening in case of a thermodynamic cycle, it is starting from a particular point 1 and it is going to some other state, and from that particular state it is coming back to the initial state. So what happens in a cycle, it's a closed diagram always. Okay, one more important thing about the thermodynamic property in this particular case, for example, if I talk about any thermodynamic property, say if I say pressure, then I can know if it is a thermodynamic cycle, the initial pressure and the final pressure will be same. There won't be any change in the pressure, because pressure is a property. Whenever we are talking about any property in case of a thermodynamic cycle, the value of the property will be same in case of a thermodynamic cycle. Whether you take temperature, volume, pressure, or say energy, so that would be same. Energy means internal energy or enthalpy. We are not talking about some the other forms of the energy, for example work and heat transfer. Work and heat transfer, that means W and Q, they are not the properties. You should always remember that W means work and Q heat transfer, they are not the properties. They depend upon the path being followed. So if the path being followed is known, then work and heat transfer will be different for different paths actually. That we will study in the next chapter, chapter number 3 actually. Okay, Now let us talk about thermodynamic equilibrium. Now this thermodynamic equilibrium is very very important concept in thermodynamics. So a system is said to exist in a state of thermodynamic equilibrium when no change in any macroscopic property is registered. So let us read the definition once again. A system is said to exist in a state of thermodynamic equilibrium when no change in any macroscopic property is registered if the system is isolated from its surroundings. So that means if you are uh, separating the system from the surroundings and you don't find any change in the state of the system, okay, if you don't find any change in the state of the system, that means the system is existing in thermodynamic equilibrium with its surroundings. Okay, so uh, what are the various conditions to be satisfied for thermodynamic equilibrium? So that is important here. A system will be in a state of thermodynamic equilibrium if the coordinates or the conditions for the following three types of the equilibrium are satisfied. So that means we have to satisfy certain conditions of equilibrium for system to be in thermodynamic equilibrium. So what are those conditions? Let us see. The first one is the mechanical equilibrium, the second one is the chemical, and the third one is the thermal equilibrium. So what is the meaning of the mechanical equilibrium? Mechanical equilibrium basically relates to pressure. Chemical equilibrium relates to the chemical composition. Thermal equilibrium relates to the temperature. So let us first of all talk about the mechanical equilibrium. In the absence of any unbalanced force within the system itself and also between the system and the surroundings, the system is said to be in a state of mechanical equilibrium. So that means if suppose we have a piston and cylinder arrangement with us, okay. If I say the pressure here is say 1.2 bar and the pressure outside is 1 bar. So do you think that the system is in mechanical equilibrium with the surroundings? No, it is not in the mechanical equilibrium. What will happen in this particular case? If the inside pressure is 1.2 bar, then the piston will move outwards. The piston will reach here and its volume will increase. It will increase till the pressure of the gas inside the system becomes 1 bar. So inside pressure is 1 bar and outside pressure is also equal to 1 bar. So both are 1 bar. Okay, so both are balancing actually. So if both are balancing, that means it's the system is in the mechanical equilibrium. Moreover, when we are talking about the mechanical equilibrium, then I can also say, suppose if I take this particular location and this particular location, then there should not be any pressure differential between these two locations. I mean to say that it should not happen that the pressure here is 1 bar and the pressure here is 2 bar. Okay, so that pressure differential should not exist within the system itself also. Only then the system is said to be in the mechanical equilibrium. That means there should not be any unbalanced forces. Now let us proceed to chemical part. If there is no chemical reaction or transfer of matter from one part of the system to the another, such as diffusion, etc., the system is said to exist in a state of chemical equilibrium. So that means it's very, very clear there should not be any chemical reaction. And second is transfer of matter from one part of the system to the another part. If such things are happening, then we say the system is not in chemical equilibrium. But for thermodynamic equilibrium to happen, there should not be any, the system should be in the chemical equilibrium actually. And the third very important part is the thermal equilibrium. So thermal equilibrium means when a system is existing in mechanical and chemical equilibrium, if it is separated from its surroundings by a diathermic wall, diathermic means which allows heat to flow, and if there is no spontaneous change in any property of the system is said to be in a state of thermal equilibrium. What does it means is, suppose if this is the system and there is a gas, okay, there is a gas, and if no heat transfer is taking place, means the value of Q is equal to 0, then means the gas is losing heat to the surroundings, that value is 0. Or if from the outside, if no heat is coming into the system, that also is equal to 0. That means It is because there is no temperature differential that is existing between the system and the surroundings. So that means the system is now in thermal equilibrium. So thermal equilibrium means temperature is equal within the system and the surroundings. So that means if this condition is also satisfied, then we will say that the thermodynamic system is in thermodynamic equilibrium. So thermodynamic equilibrium means thermodynamic equilibrium is, once again telling you, there should be thermal equilibrium. So you should not confuse yourself with thermodynamic and thermal equilibrium. So it is thermal equilibrium and chemical equilibrium and mechanical equilibrium. So if three conditions are existing simultaneously, then we will say that the system is in thermodynamic equilibrium. Now let us proceed to the next topic, which is quasi-static process. So quasi-static process, it is a very important concept in thermodynamics. This process is also known as a reversible process. A reversible process. Now let us see this particular diagram here. So what we have done here, we have shown a piston and cylinder arrangement here. This is the you can say cylinder. It is not written here. It is cylinder. Okay, and this is the piston, as you can see it here. This is the piston part, and on the piston we have put a weight here. Okay, this weight could be, say, I can say it is 100 newtons. Okay, now you can say under this particular weight, what is happening, you can see that this particular gas is existing at a particular pressure P1, and its volume is V1 and temperature is T1. So this is the state coordinates actually. The gas is existing at pressure P1, temperature T1 and volume V1, and there is a weight over it which is equal to 100 newtons. Okay, now what I will do, I suddenly lift this weight, I remove this weight. Okay, I remove this weight. Okay, before that, when I say if I have not removed this weight, okay, forget about this part first of all. Now the pressure in the gas is P1, V1 and T1. Okay, so this is one of the equilibrium state of the gas actually under this particular pressure, because the pressure which is acting here now is balanced by the pressure here. Whatever is the temperature outside, same is the temperature inside. Okay, so this is a sort of equilibrium state and it is represented here by point number 1. Now what happens, the moment I lift this weight, what will happen? Because now the pressure which is exerted outside is removed. The moment I remove it, the piston will suddenly move to this final state. This is the final state. This was the initial state actually. Okay. Now it moves to this particular state. And there are stops actually. This is the position of the piston now. So now it has been stopped here with the help of these stops. Whatever now the conditions are, now you can say it is P2, V2 and T2. Now at this moment, what is happening, the system is now also in a equilibrium state actually. So this state is shown here by point number 2, because the volume has increased, whereas the pressure has reduced. We are not worried about the temperature, what is happening to the temperature, but we know, yes, the state point 1 is a thermodynamic equilibrium state, thermodynamic equilibrium state, and here also state point 2 is a thermodynamic equilibrium state. So both these states are in thermodynamic equilibrium. But what has happened? What can you say about the intermediate states? There are infinite number of the intermediate states between 1 and 2. But we know that only the state number 1 and state number 2 are basically thermodynamic equilibrium states. Okay, so the process which has occurred in this particular case is a spontaneous process. So what is the type of the process? It is a spontaneous process. It is a spontaneous process. And in case of a spontaneous process, I know that the initial condition is the thermodynamic equilibrium conditions and the final condition is also thermodynamic equilibrium conditions. I do not know the path of the system, means I don't know from where the through which intermediate states the system has passed. So that is why this line which is shown here is shown as dotted. Dotted means I do not know the path of the system. Okay, so this dotted line could have been drawn like this also. Okay, it could have been drawn like this also. Suppose uh, I can say I could have drawn it like this also. Okay, so because I do not know what is the intermediate states. Okay, because this is a spontaneous process, so this is not a reversible process, this is not a quasi static process. If you see the name of the process, static means nearly stationary. Quasi means almost. Quasi actually means almost, and static stands for stationary. Almost stationary process. Okay, so let us proceed to next slide actually. Now Now I will tell you about the quasi-static process. Now what has happened now? The same system, same piston and cylinder system, I have considered the system boundary is shown. The piston is here. Now what is the difference between the previous case and this case? In the previous case, the weight was 100 Newton. Now also it is 100 Newton. Okay. Now what I will do, I will remove very small weights from it. Suppose the first weight which I remove from this particular over this, which is kept over this piston, is I will remove say 0.01 into 10 raised to power minus 100 Newton. Now this is a very small weight. So what will happen? I know this is the initial condition. This is the initial condition. Now because I have removed a very small weight, this very small weight, so what will happen to the state? The state will be very near to the state point number 1. So the piston will reach here. Then once again I will remove one more weight. The piston will move a little bit downwards. Okay, a little bit expansion will take place. Then similarly I will keep on removing all the weights slowly, very slowly, till the total weight removed is 100 newtons and piston has reached at this particular location. So what will happen in this particular no case? I know each and every point through which the system has passed. So there are infinite states, infinite number of the states. I know each about each and every state through which the system has gone. So then I know the final state also. So all these states are nearly equilibrium states because I have removed the weights very slowly. So such a process in which the departure from the initial state is very small, that process is actually known as the quasi-static process, because I know that each of the state is now in the equilibrium. Actually it is almost equilibrium. Okay, it is not totally equilibrium, but quasi-equilibrium means almost equilibrium state is there. Okay, so let us see the definition. A process in which the departure of the state of the system from the thermodynamic equilibrium state is infinitesimally small, means very small, so that every state passed through by the system will be an equilibrium state. Then such a process is known as quasi-static process. Such a process, which is a locus of all equilibrium points passed through by the system, is known as quasi-static process. Quasi meaning almost. And what is the characteristic feature of this process? Infinite slowness is the characteristic feature of a quasi-static process. A quasi-static process is thus a succession of equilibrium states. A quasi-static process is also called a reversible process. So this is very important. The one thing which is important is infinite slowness is the feature of the quasi-static process. As I told you, we are removing the weights one by one, and each weight which is removed from the piston is very small. That is the reason that each of the state through which the system is passing can be said to be a quasi-equilibrium state. So such a process is also known as a reversible process. Okay. So all the processes for which we will be doing the analysis in thermodynamics here, they will be considered as the quasi-static process. Means we know through which means through which path they are passing. Okay, if I know that a process is a if I say isobaric process, Okay, if it is a isobaric process, it will be only isobaric if I know that each point through which the system is passing is of constant pressure. A constant pressure process can be shown like this. Okay, if it is like this from 1 to 2, if it is going like this, then I know that at this particular point the pressure is P, at this particular point the pressure is P, this particular point pressure is P, this particular point the pressure is P, and so on. So each point the pressure is P. Only then this process is a reversible process or a quasi-static process. So whatever the process I have talked about, constant volume, constant pressure, constant temperature, polytropic or reversible adiabatic process, they are considered to be quasi-static process. Only then we can do the analysis part. Like in your chemistry in your 11th or 12th class, you study about the irreversible work and the reversible work, but they don't tell you the difference between the reversible and the irreversible. Okay, so here it is important to understand that every reversible process is basically quasi-static process, and it is going to happen very very slowly. So infinite slowness is the feature of a quasi-static process that you should understand. Now let us talk about.
सर
Yes,
सर एक प्रोसेस को क्वासी स्टैटिक तभी कह सकते हैं ना जब अगर हर पॉइंट पे हमें उसकी प्रॉपर्टीज पता हो.
correct. That is why I am telling you that each point, for example, I took the example of constant pressure process. I told you that at each point the pressure and temperature and volume of the system are known, and in this particular case the pressure is constant throughout if it is isobaric process. If it is a isothermal process, the temperature at each of the points will be known to us. Okay, and each state is also known to us through which the system is passing. If the state is not known, if the intermediate states of the system are not known to me, then it is never a quasi-static process, it is a spontaneous process then. Okay,
ओके सर.
okay. Now let us now it's very very simple. Now you know about the units and the dimensions part also. I will go a little bit fast here. Mass, you know about the mass, it is the quantity of the matter contained in a substance, and you know its unit is kgs. Let us talk about the force. You know force about the force also. It is defined on the basis of Newton's second law of motion, and we say that the rate of change of momentum is called force. You know that F is directly proportional to rate of change of momentum, mass into velocity. Then I can say that F is equal to m dv by dt plus v dm by dt. Because we are considering that the mass is conserved, so this quantity is 0. V dm by dt will be 0, and I am left with this particular equation, and I know that this quantity dv by dt is equal to acceleration. So force is equal to mass into acceleration. So once the force is equal to mass into acceleration, I know that the unit of mass is kgs. For acceleration it is meter per second square, and I know the SI unit of force also, it is equal to newtons. So what is this Newton actually? This is equal to 1 kg into 1 meter square per second, 1 meter per second square. So this is the unit of acceleration, this is the unit of mass. Multiplying both, I get 1. So that means 1 kg per meter second square is equal to 1 Newton. Okay, this you should always remember. So this is 1 Newton. So I can say the unit of force is either Newton or kilonewton. And you know about the 1 Newton also. A force of 1 Newton produces an acceleration of 1 meter per second square when applied to a mass of 1 kg. This is already known to you. So important thing here is equal to F is equal to ma, and unit of force is Newton. Then we can discuss about weight. Weight is the force with which a body is attracted towards the center of earth. So once again I am highlighting force. So weight is nothing but force. So what should be the unit of force? Its unit should be Newton only, because it's force only. And what is weight equal to? Weight is the product of mass and the local gravitational acceleration g. So W is equal to m into g. This is already known to you. And what is the value of g? You have been using a value of g which is equal to 9.81, but actually the value of g is this 9.80665 meter per second square. The mass of a substance remains constant with elevation, but its weight varies with elevation. You know, if you are weighing say 600 Newton on Earth, then on Moon you will be weighing I think based on the gravity of the moon, 1/6 is the gravity of the moon. So your weight will reduce, but your mass will remain same. Okay. So once again, weight is the force and its unit is Newton. So that you should remember. Then come energy. Energy is the capacity to do work, and its SI unit is Newton meter, or and when I take Newton meter, it becomes joule. So 1 Newton meter is equal to 1 joule. SI units for energy could be kilojoules, megajoules. 1 kilojoule is 1,000 joules. 1 megajoule will be equal to 10 raised to power 6 joules. Okay, so that you should remember. Then let us talk about the pressure. Pressure. Pressure is the force per unit normal component of the uh, force per normal component. This definition is written wrongly actually. It is the normal component of the force per unit area. Okay, so pressure is the normal component of the force per unit area. So you can see here, suppose this is a surface and its area is A, its cross sectional area is A. Okay, and we are applying the force over it at an angle theta with the vertical direction. This is the angle theta with the vertical direction. So what I have to do to calculate the pressure over this particular area, I have to take the normal component of the force, which is equal to F cos theta divided by the cross sectional area A. So this will give us the value of the pressure which is acting over this particular surface. Now what is the SI unit of pressure? You can see it is the force. So force has a unit which is equal to Newton. Area has a unit which is equal to Newton per meter square. And you should always remember that 1 Newton per meter square is equal to 1 Pascal. Now, what is the SI unit of pressure? Pressure has the SI units which is equal to Pascal, which is nothing but 1 Newton per meter square. Okay, Pascal is Newton per meter square. Kilopascal will go for 1,000 pascals because kilo means 10 raised to power 3. You should always notice that this K is small. Okay, it's a lowercase letter. So K means 10 raised to power 3. If it is a capital K, it is the unit of the temperature. It is Kelvin actually. So you should never use small capital K when you are writing. Suppose if you are writing kg, so it is actually Kelvin gram, not kilogram. So always mind it, kilogram is small k into g. So kilogram is kg. Okay, unit of mass. So another unit of pressure is bar. Bar stands for 10 raised to power 5 Pascal, which is equal to 100 kilopascals, which is equal to zero point 0.1 megapascal. So you should remember all these units because we will be using these units extensively when we will be doing the numerical problems. So 1 megapascal is 10 raised to power 3 kilopascals, which is equal to 10 raised to power 6 pascals. So once again, SI units of pressure are Pascal, kilopascal, bar, megapascal, etc. And you know the Pascal's law, pressure P at a point in a fluid in equilibrium is same in all the directions. The SI unit of is Pascal, which is the force 1 Newton acting on an area of 1 meter square. So here we have defined 1 Pascal actually. So 1 Pascal is 1 Newton per unit area. Okay. So this I have already told you all these things. This is wrong. This is 10 raised to power 5 Pascal. 1 bar is equal to 10 raised to power 5 Pascal, 100 kilopascal, zero point 0.1 megapascal. Now this is very, very important. Standard atmospheric pressure. Standard atmospheric pressure means the pressure which is acting on us. Okay, and that value is 1 atmosphere. 1 atmosphere is the pressure which is exerted by the air on us or on the earth actually. So it is equal to 101.325 kilopascal, which is also equal to 1.01325 bar. So you have to remember this value. You have to mug up this value. Nobody is going to tell you what is the value of the 1 atmosphere if it comes in the question. You should remember it. And it is equivalent to 760 millimeter of mercury column at sea level. Okay. Now, how to calculate or how to prove that this 1 atmosphere is equal to 101.325 kilopascals? Okay. So we know that when we calculate the pressure, pressure has the formula rho into G into H. Now, because we are talking about the column of the mercury, 760 millimeter column of the mercury. So I will be taking all the values corresponding to mercury actually. So atmospheric pressure has to be calculated on the column of mercury actually, and the level H value is actually equal to 760 millimeter. So what is the value of rho? Rho for mercury is this value, 1000 kg per meter cube into 13.595. This 13.595 is the specific gravity. It is specific gravity of mercury. You know, you write it as you might have heard about that the specific gravity of the mercury is 13.6. Yes, that is the rounded off value. Here we are taking 13.595, which is the exact value, and multiplying this value of specific gravity by the density of the water, which is 1000 kg per meter cube, I can get the value of the density of the mercury. Density of the mercury multiplied by the acceleration due to gravity, which is 9.80665 meter per second square, multiplied by the height of the column of the mercury, which is 0.76 meter, I will get a value of atmospheric pressure, which is equal to 101325 Pascal. So calculating this value in kilopascal, you divide by 1000 and you get this particular value. If you divide this value by 10 raised to power 5, you will get the value in bar, which is equal to 1.01325 bar. So once again, the pressure value is equal to 1.01325 bar. It is equal to 101.325 kilopascal. It is equal to 101.325 pascal. So you have to mug up this value. This should always be known to you. Nobody is going to tell you. Now let us talk about the other two types of the pressures. One pressure is gauge pressure, other is vacuum pressure, and the last one is the absolute pressure. Okay, so let us try to see this chart actually, which is shown here. This is very important chart. So you can see here I am representing on the y-axis, I am representing the pressure. So on x-axis, this is the x-axis. This is not showing any parameter or the physical quantity. I am just showing that this horizontal line is actually showing a pressure value which is equal to 0. Okay, this is a value which is equal to 0. And this line, as you can see here, this is showing the atmospheric pressure. That means this value is 1.01325 bar. Okay, now if you have a pressure which is above this atmospheric pressure, suppose point A, like this, it is shown here. Okay, this is the point. Now this is above it, this is above the atmospheric pressure line. So the pressure which is just above the atmospheric pressure line is known as the gauge pressure. So that means this value of the pressure from here with reference to the atmospheric pressure is known as the gauge pressure. Okay, this is the gauge pressure. So let us see. What I am going to write is, see this particular first equation you see here. PA absolute. What is PA absolute? It is equal to gauge pressure at A plus atmospheric pressure. Okay, so once again, you see it here. This is the absolute pressure when I am taking the pressure with reference to zero pressure. The value is known as the absolute pressure, and this is the absolute pressure from this particular point up to this particular point. This is known as the absolute pressure at point number A, and it is equal to sum of gauge pressure, which is equal to this value with reference to the atmospheric pressure. This is the gauge pressure at A plus atmospheric pressure. This is the value of the atmospheric pressure. So this is atmospheric pressure plus this is the gauge pressure. So the sum of atmospheric pressure and gauge pressure gives us the absolute value of the pressure at point number A. Now I can have another point like B. Now you see here, point number B is below the atmospheric pressure line. This is the atmospheric pressure line. So it is this value, it is the vacuum. So this pressure, the pressure at point number B is this much below the atmospheric pressure. So that means pressure at B is the pressure at B is the vacuum pressure basically. Okay, the pressure is below atmospheric pressure. So that means there is vacuum in the system. So if I have to calculate the pressure, absolute pressure at point B, then with reference to atmospheric pressure, this is the height which equals to the absolute pressure at point number B. So what I will write, absolute pressure at point number B is equal to atmospheric pressure minus vacuum pressure. Okay, so these are the two important concepts. Then we can go for the gauge pressure. Now, gauge pressure is measured with the help of a gauge or a pressure measuring instrument. So we need to have a some sort of instrument with the help of which we measure the gauge pressure. For example, if it is a tire, if you are going on a drive and you go to a petrol pump, there you go for the air, means filling of air in your tire, the tires of the cars. Then you see the gauge. So you say to that person that you fill it up to 33 psi. So that 33 psi is the gauge pressure actually. Okay, so you should always remember that the pressure in an system, if it is open, then it should be atmospheric pressure, and if it is attached to a gauge and it is measuring a particular value, then it would be the gauge pressure. So we can have gauge for measuring the gauge pressure as well as the vacuum pressure. So
So can you please explain vacuum pressure once more? Vacuum pressure.
see, vacuum pressure is nothing. For example, this is the atmospheric pressure value. Okay, it is equal to 1.01325 bar. Okay, and suppose this is the system here. Suppose this is a container where the pressure, absolute pressure P absolute is say zero point 0.8 bar. Okay, this is the pressure here. So zero point 0.8 I can represent here. This is the value which is equal to zero point 0.8. Okay, and this value, this pressure with this is equal to zero. So with reference zero pressure level, this is the absolute pressure. If I say this point is C, then this is the absolute pressure at point number C. So that means what is the level of the vacuum? This is the level of the vacuum. This is P vacuum. Okay, this is the vacuum actually. So if I have to calculate the absolute pressure at point number C, what I will write, pressure at C is equal to P atmospheric minus P absolute at point number C. Is it clear now?
Yes, sir. Yes, sir.
Okay, so we have two equations now. The first one is P absolute is equal to P atmospheric plus P gauge, because gauge pressure is always above the atmospheric pressure. Okay, and P absolute, the second is P atmospheric minus P vacuum. Okay, so these are some of the gauges which are shown here, which can be used for the measurement of the pressure. The first gauge is the Bourdon tube pressure gauge. This one, this is the U tube manometers which are used for the measurement of the pressure of the liquids. Okay, then density, you know, it is equal to mass per unit volume. So unit is kg per meter cube. If I talk about the specific volume, it is 1 by rho, which is equal to reciprocal of the density. It is equal to V by M. So unit is meters cube per kg. Energy capacity to do work, I have already discussed about it. Work, you know, it is equal to dot product of force and displacement. Unit is Newton meter. Newton meter stands for joule. Okay, power, if you want to calculate, it is equal to energy per unit time. So energy has the unit which is equal to joule per second, and joule per second is nothing but watts. Okay, so I can have other units for power also. For example, I can go for kilowatts. So 1 kilowatt will be equal to 10 raised to power 3 watts. 1 megawatt will be equal to 10 raised to power 6 watts, which is equal to 10 raised to power 3 kilowatts. Okay, so this was about units and dimensions. And this is the gas equation. PV is equal to MRT, where P is the pressure, V is the volume, M is the mass, R is the characteristic gas constant, T is the temperature. Okay, you know about it. You have heard about the equation PV is equal to nRT. Now, in this particular equation and this particular equation, there is a little bit of difference. Here, N used to be number of moles, R used to be universal gas constant, and V used to be volume, P used to be pressure, and T used to be temperature. Here, the only difference is this M is the mass now. I have written it here. M is the mass, and R is not the universal gas constant, rather, it is characteristic gas constant. And what is the relationship between universal and characteristic gas constant? This is the value of universal gas constant. This is universal gas constant divided by the molecular weight. You will get the value of the characteristic gas constant R here. Okay. So you know the value of the universal gas constant, it is 8.3143 kilojoules per kilomole per Kelvin. Okay. So, yes,
Sir, sir, I have question.
yes.
Sir, what are the factors affecting gauge pressure in any system?
अभी उसके बारे में ज़्यादा मत सोचो. See, gauge pressure, if you are filling more amount of the substance in a particular volume, the gauge
Yeah,
pressure will increase. For example, if you have a tire, okay,
yeah,
if
yes, yes.
you remove all the air, what is the pressure inside the tire then?
Increase higher.
No, no. My question is, suppose there is a valve in the tire also. Whether you have a cycle or you have a bike or you have a car, if you remove that valve, okay, what is the pressure inside the tire? Is there any air in the tire?
Not sir, zero.
There won't be no any air. There won't be any air
Atmo
in the tire.
Atmospheric air.
Atmospheric pressure.
Atmospheric pressure will be there, sir.
So when you fill the tire, the gauge, whatever the pressure it shows, is the gauge pressure. Okay, that is above the atmospheric pressure. Whenever you go to the petrol pump, you ask the petrol pump person who is filling the air that you keep a pressure of 33 psi or 34 psi or 35 psi or 25 psi. So you are talking about the gauge pressure. So it is over and above the atmospheric pressure. So more the volume, more the mass of the air you put into the same volume, the pressure will increase actually. The gauge pressure will increase. The total absolute pressure will increase.
Oh, oh,
Okay.
okay, sir. Okay, sir.
Now,
Thank you, sir.
now switch off your mic. Now this is the universal gas constant having a value 8.3143 and the molecular weight. So you can see here, this is the characteristic gas constant for oxygen. So for oxygen, molecular weight is 32. So this is the value of the um, uh, characteristic gas constant for the oxygen. If you happen to calculate the value of R, which is the characteristic gas constant for the air, the value is 0.287 kilojoules per kg per Kelvin, and you have to remember it. You have to remember it. Nobody is going to tell you. Probably sometimes the question may come where the air is given as the substance, and then the value of R won't be given. Okay, so you have to remember this particular value. It is 0.287 kilojoules per kg Kelvin. Now I have a question for you people. Uh, this question you can note down and you have to solve this question. You can take a print screen or you can write this question. What I have shown here is there is a cylindrical container. Okay, there is a cylindrical container which is containing hydrogen gas, H2 gas. Its diameter is 20 centimeter. Its length is 150 centimeter. There is a pressure gauge which is showing a pressure of 20 bar reading. There is a temperature gauge which is showing a temperature of 83 degrees Celsius, and you will have to calculate the mass in kgs for the hydrogen gas. And what you do, you just give 10 minutes to yourself. Okay, because no, it's not a offline class. Normally I will not give more than 5 to 7 minutes to a particular student to solve this numerical problem. So give yourself between 5 to 10 minutes and see whether you are able to solve this numerical problem. Okay, so this is a question for you people. You solve this and tell me what is your answer, but don't take more than 5 to 10 minutes, and be honest to yourself. I would like to ask you in the next class what you did actually. Okay, so this is for all today, and just wait for 2-3 minutes. I will take your attendance.